Okay, so let's look at a very simple and intuitive enhancement to the reinforced algorithm that actually will help quite significantly in many cases. And this is adding some baseline to the reinforced update. I'll explain this in a second. So first of all, let's see the motivation behind this enhancement. So let's imagine a domain with two possible episode trajectories, two possible rollouts for the Monte Carlo approach. One, if you follow a specific policy, one trajectory will get you a G value, a sum of discounted reward of 1001 reward. If however you choose some different action initially, it might get you to the second trajectory, another trajectory, which results in a sum of discounted reward which is 1000. Right? So it's a very small difference, but both of them are very high sum of discounted reward. Let's further assume that all of the reward is just provided at the last time step. Okay, it's important for the sake of the example. So if we follow the reinforced algorithm, where we update the policy proportional to the observed sum of discounted return, we can ask, how will the policy be updated after sampling each one of these trajectories? So for all of the actions drawn for policy number 1, will we increase or decrease the probability of taking those actions?
Increase.
Increase, right, but quite a lot, 1001. And what about all of the actions taken in trajectory number 2?
It'll also increase, but not as much.
But almost as much, 1001 times over 1000, right? It's practically by the same amount. So, although we just saw that trajectory number 1 was better compared to trajectory number 2, when we do the policy update after visiting both trajectories, we actually increase the actions that we're taking in each one of the trajectories, but by about the same amount, right? 1001 over 1000, it's the proportion is about the same. But how should we have updated the trajectories, the actions probabilities?
Preferred 1 much more over 2.
So we should have actually increased the probability of choosing
1.
all of the actions in trajectory 1 and somehow decrease all of the probabilities of taking the actions in trajectory number 2. So we should probably intuitively do the following updates, right? Increase all of the actions taken in trajectory number 1 and decrease all of the actions in trajectory number 2. Slightly, right? You might say the difference is not high, it's not significant here. It might be significant, it might be not, right? We won't go into reward scaling. That's a different topic. We'll discuss that later. How can we address this gap? Normalizing the G values, right?
Yeah.
So ideally we would like to probably this to be transformed to be probably plus 0.5 and this to be minus 0.5. Right? Just scale the rewards and we'll get the appropriate gradients, or the gradients that we think are more appropriate. And indeed, this is the idea behind policy gradient with a baseline. So we normalize the returns with some baseline. We call it B of S. The baseline is now, of course, it might be different for each one of these states. But the question that you should be asking now is, can we do that? I mean, we did a very long derivation for the policy gradient expression. And now I'm telling you, yeah, let's just add some kind of another term here and everything is fine. But you might ask, correctly so, hey, listen, we might be breaking stuff here. And specifically, can we subtract this value from our gradient, right? So if you break down what's going on here, so you multiply b of s by grad pi. If you just try to how do you call it? Separate out the new what you added to the original gradient term. So it will be minus bs times grad pi s times mu s. So how are we allowed to subtract this term from the original term that we computed? Well, yes, we are allowed to do that. As long as your baseline function, the b of s, is not a function of the specific action that you took. As long as this is the case, then the expression that we just added is simply, well, you can take the b of s, right, this function, out. If it's not a function of a, you can take it outside of the summation, and then it's just b of s multiplied by the gradient of the summation of the probability under each one of the possible actions. And this is simply the b of s term multiplied by the gradient of 1. Why is it a gradient of 1? Because the summation of the probabilities of all of the actions must be 1, right? And this is simply 0. So yes, we didn't change anything by adding a baseline that is not a function of the action. So indeed, we can define another version of the reinforced algorithm that includes a baseline, and it's still fine. We're still following the math derivation that we've seen previously. How should we set that baseline? So we did this before, right? With the bandit for the bandit problem, we also used the baseline to normalize our Q estimations there. In the bandit case, it was we used the baseline, which was the average of the rewards seen so far, but it was stateless. It was always for the same state, we just have a single state. For MDPs, the baseline should be different for each state, right? It should be a function of the state. In some states, all actions have high Q values, and we need a high baseline to differentiate the higher values actions from the less highly valued actions. But it might be the case that in other states, all actions will have low values. And so we need a low baseline, obviously, to normalize the returns. What would be the equivalent of the average rewards, in the bandit case, for a given state in an MDP? Average over all of the actions, right?
Over all the actions.
In a given state, in a specific state. So what would be the average over actions?
So it would be a given state, not like future states.
A given state.
Okay.
But average, so the average return.
So then just the value.
The state value, yeah. Right, that's correct. So the state value can be equivalent-ish to the previous normalization term that we used for the bandit case. And indeed, we'll use the state value as the normalizing factor. And now we see that actions that improve on the current policy are encouraged, right? If the Q value for a specific action is higher than the current state evaluation, well, then it's a good action to take. It's better than the current, increasing or taking this action over the current policy is good, is beneficial for us. However, if your actions that have a Q values that is lower should probably be discouraged. Okay? The Q value minus the state value is also known as the advantage of action A in state S. This is known as the advantage function. This is something that we'll revisit later on. We'll see the advantage function also in other algorithms, but it's simply defined as this way. Right, we're representing the advantage of taking action A, specifically in state S, over following the current policy that we have. How can we learn the state value for state S under the current policy? So on policy learning of the state value for state S.
Train a critic?
we didn't say what a critic is so far, and in this case it's not technically a critic, but never mind, we'll discuss it again later on. But we can train another approximator, right? We can learn it in a tabular setting, the state values, or train another approximator to learn the state values. But normally, right now, we already went to large state spaces and we discussed the values of approximators. We're usually going to use an approximator to try to approximate the state value in a given state, for any state. So we'll add another approximator on top of the policy approximation. And this is indeed the idea behind reinforce with baseline. So you can see now that this is, well, the same algorithm, only now we both update the policy algorithm as before, but now we also update the value, the state value approximator. Okay, now in order to differentiate the tunable parameters, so we use theta in this case, in this pseudocode, also from the textbook. Theta will be the approximation parameters for our policy, while W will be our approximation parameters for the state value approximator. Okay, how do we update the state value approximator? Similar to what we've seen before, using TD learning, one-step TD learning, where small delta is the one-step TD error. Actually, it's not a one-step TD learning. This is a Monte Carlo based update, right? So it's actually in these pseudocodes, it can be one-step TD learning, we can change this, but in this case, if we're doing Monte Carlo, if we're using a Monte Carlo approach, we'll take the full return and use that as our small delta, as our error, TD error. And indeed, if we now apply reinforce with a baseline, we can see much faster learning. So for this small state space now, I would expect something like this, a very, very quick learning, right? As we said before, we would expect to perform much faster learning compared to, for this very simple problem. By the way, in this case now we have different learning rates for the policy and for the state value approximator. These are just optimized values that were found for this algorithm in this case. But you can see that they are very different, like 3 orders of magnitudes different. That might be the case. These are the learning rate is usually optimized empirically. You just have to try different values and see what works best. And as we can see here, they might be different for each one of your approximation functions.